force concept inventory. So everybody knows that. I don't need to talk about that. But, and you know how it's used. How many of you are familiar with this work of hate where you combine all the, okay, so not a lot of you aren't. So, okay, so this is important for you to know. So this is basically, you know, using the force concept inventory, giving it the beginning of the term and the end of the term, and then just seeing the fraction of the question the students got wrong at the beginning, do they get right at the end, and using that as a measure of what they learned. And if you look at the average of this fractional gain over all the students in the class, it turns out there's a remarkably robust result that comes out, which, and Kate has this one paper where you tabulate this for a whole bunch of things, but we've got lots of other data much the same. And what it shows is that basically in this on the average, the fraction gain learned for a traditionally taught lecture course just basically doesn't get above 0.3. The thing that's remarkable about this is this shows up independent of other measures of lecture quality, class size, institution. You know, there's community colleges and Harvard University in that data. It says, and we now see this across other disciplines, other levels. It says it's just fundamentally the traditional lecture approach is simply not an effective way of learning conceptual mastery, learning to use concepts like an expert, and going back to the research on cognitive psychology, you can understand exactly why. So all these improved methods you're learning about, where the students are much more explicitly practicing thinking about these and using these things, then they consistently get up in sort of factors of 2. So again, lots of solid data really supporting this idea of conceptual mastery. They're just fundamentally better ways of lecturing to the students. Here's an article that probably most of you haven't seen, but I think it's really a nice article. It's an American Journal of Physics because it looked at a whole bunch of instructors across many sections. This was work done at Cal Poly, and it simply had them change how they taught and saw what that turned into in terms of student learning outcomes. Again, they were using slightly different, I think they used the MMCE, but a slightly different test of conceptual mastery of force of motion. And they had collected data over a bunch of years and a bunch of instructors, and then using the lecture approach, and they were a little below 0.3, so they were doing well by traditional lecturing, but just consistent with the things I talked about. And then they switched over to a studio physics approach, which in their context meant that they had a bunch of carefully developed, prescribed student activities, and the instructors were then facilitating the students to actively work through all these activities. And what they saw was that then when they measured the conceptual learning gains, everybody jumped up to about 0.6. And actually, if you do, they don't do this in the paper, but I got some of their data and did it myself. If you do a fine, more careful statistical analysis of this, you find, in fact, that within the statistical uncertainties of the class, number of students in the class, there is no difference between any of the instructors here. They're all equivalent. And this just emphasizes the point that I've been making, that it's really the mental activities of the students, what goes on in the student's brain, that really dominate the learning rather than what the student does. And so to the extent that was standardized here, you get standardized learning gains. But you can also see that it's a tremendous improvement in what students are learning. And for some instructors, it's really amazing. I mean, I don't know who this is, but I'm sort of looking at their, pre-post. But stop to think about this when you're discussing this with other faculty and so on. This is an instructor who, they didn't get hit by a bolt of lightning. They didn't go through a religious transformation. They simply were given a different way to teach physics, and their students learned 6 times more. So that's pretty amazing. But that's also pretty strong evidence for the view of, teaching is a sort of a innate art as opposed to something you can learn to do. This is pretty clear that you can learn to do a lot better. Okay, I'll just finish with one final example that's something I was involved a little bit with, and that was focusing, the previous things were really the whole class, so what went on in the classroom, homework, exams, etc. This was really focusing on just the learning that takes place in the classroom itself. And we focused on that in part because even though that's not actually where I believe most of the student learning takes place, that's what the faculty, the instructors pay the most attention to, what they're doing in front of students. And so, so this looked at the giant class of all the engineers and UBC have to take the same introductory physics class with a bunch of sections of 270 students each. And in the control section, it was a standard lecture class. It was given by a very experienced professor at a high student rating. And in fact, it was already a little bit better than standard lecture, and then he did use clickers, but he didn't have any student discussion. They were just occasionally used as sort of a summative testing process, which is the way most people use clickers when they got them for the first time. And then the experimental section was actually taught by a physics postdoc, but had been through the program that I run in training them to use these more effective teaching methods and these principles of effective teaching. And so they got together and they came up with an identical set of learning objectives that they would cover in exactly the same amount of class time as 1 week of classes, and then test how well the students had achieved these learning objectives on the exam that was given immediately following the 1 week of classes. So they didn't have homework assignments, they didn't have any exams, any of those things, really probing what they took away from those classes. And so here's the histogram from the results on that exam. So the red is was in this standard lecture class from this highly rated by students professor, and the white is the experimental section. And a couple of things. First, I should point out, to keep this as objective as possible, it's making me a multiple choice exam, and so random guessing gives you there, so that gives you a perspective on just how much learning students are actually achieving from listening to a reasonably good lecturer. But the more important point I want to emphasize here, because this comes up in a lot of discussions about teaching and teaching methods, which is that, this makes the point that, as does other evidence, but this makes it particularly dramatically, that the entire distribution of students moved up, right? And so this doesn't mean, so what this shows is these teaching methods, these aren't something that just preferentially help the best students, preferentially help the worst students. This is much better for every student who has a human brain, basically, because this is how the human brain learns. And so you can get away from, this kind of data can get away from the arguments about, and I'm going to hurt the best students. And so as long as they got human brains, you'll be pretty safe in assuming it's going to happen. I don't have time to go through lots of other stuff. I'm just going to give you sort of components of effective teaching that come from reviewing very broad as possible research that really apply to all levels and all settings. And so I'll just kind of leave you with this message without going into detail. What I've been really talking about here is very much this explicit, authentic practice of expert-like thinking, the kind of tasks you have to have, the kind of feedback to make that effective. But there's some other things that are really important, knowing learning to support that. There's motivation, and which I'll talk about more in a minute. And there's connecting with the student's prior thinking. I mean, if you get into the mode of thinking about learning as really development of a brain, you need to know where that brain's starting from. You have to have the appropriate tasks, you have the appropriate things to motivate that brain to put in the effort. And so that recognizing and dealing with prior thinking is really critical here. And then there's some other stuff that comes from a completely different area, which is just knowing how the mind, the basic level processes and learns and remembers information. And this is stuff that's really well studied, but really grossly neglected in a lot of educational practices. On the limitations on the brain and short-term stuff and achieving long-term retention. And although I'm not going to go into this stuff here, I will say that I think I gave to Bob, and you probably should have the materials you have, a packet or some files on a course transformation guide for, if you want to take a course and transform it to be completely different and better, putting in place all the research on learning. In there's more references, more discussion about some of these issues in as brief a way as I could make. And then also sets of specific strategies about, in a course, how you actually embody the different elements in this. And I also should make a point that up in 1 and 2 are really, so this gets in, this is where all your issues of diversity, where I mean that in the broadest general sense, the fact that one student's different from another. That's really where, previous experience, educational experiences, cultural values, etc., all come in up at that level, really. But that doesn't mean they're not important. Okay, so I'm going to talk a little more about just one of these aspects of what research tells us about this, looking at motivation, and then some work that my group has done on looking attitudes and perceptions about physics and how it's learned, because those couple in strongly actually to motivation. I have to say, there's no particular reason to focus on this one, except that I was just annoyed recently again by Lillian McDermott dismissing motivation as something that physics education research shouldn't be paying attention to. To me, that's like, if you're in the airline maintenance business, you say, oh, but anything attached to the left wing of the airplane doesn't belong in aircraft maintenance. It's just such a fundamental, important point of learning that I'm going to tell you a little bit about what we know about it, how to prove it, why it's important. In fact, the cognitive psychology research in looking at this on expertise development, their strongest predictive elements that they can find of who's going to become more expert. I said at the beginning, these kind of measures of ability, talent, they can't find that these have any predictive, predictive value. But the strongest one is actually measures of motivation. That seems to be, and okay, you really shouldn't need research to tell you that. That if somebody doesn't want to learn something, they're not going to learn it. And somebody who really wants to learn something, they're going to learn it. Okay, so it's an absolutely fundamental element to learning. It's important that we pay attention to it, and if you pay attention to it with your students. So, it is complicated in any particular case because it depends on the individual, but I'll give you a few basic things that show over and over again in the research on how to enhance motivation to learn.